All right, welcome back everybody. So today is a video on FlowNets and it's quite a bit of material and I try to keep it at around 10 minutes, so let's get to it. So you have an example of a FlowNet here at the bottom of your screen, and really they're just a description of the flow inside a subsurface domain, right? So this is really just solving the Laplace equation, and the Laplace equation, if you remember, is the second derivative of head equals 0. So this is the simplest form of flow equation that we've seen so far, right? The one that is at steady state and doesn't have any source or sink term, right? So the very basic flow equation. So we've seen how to solve this in finite difference. Analytically, we've seen mathematical solutions. Here's a different take on it, and that used to be very useful in engineering. Because with a FlowNet, you can calculate, the pressure at any point in the subsurface. You can calculate the flow under a structure. So we'll see an example for a dam. So there's a lot of useful quantities you can calculate sort of quick just by drawing basically on a domain. And we'll see how to do this now. Here's another example using our finite difference code in Excel. And you can see here all those color bands correspond to equipotential. Right? And you can see how the water would flow perpendicular to those lines under this dam here and back out at the river. So there's a reservoir here and a river flowing down here. And so the flow is from the reservoir under the structure into the river. And then again, that can cause all kinds of issues. If you have, for example, too much pressure here, you can have erosion and instability. So all those things you can calculate with a FlowNet. So here's from your book from Feather, right? A list of, the recipe on how to draw those things. And I really like this little example on the right-hand side because that really tells you how to do it, basically. So here you have a 40 feet and a 24 feet boundaries. And again, remember, this is exactly like the Excel domain, the 2D domain that I've shown you over and over here, where you have a fixed boundary left and right, and then a no-flow boundary top and bottom. So it's exactly the same. So you start by drawing your flow lines. Usually, I would say 3, maybe 4 sometimes if you have a large domain, but you don't want to do any more than 4 typically. That's just from experience. Don't do many. That's just complicates things. So you have 3 flow lines, and then you can see at the bottom here, what you do then is draw the equipotentials. And here is this illustration is really good because it really shows you that typically what you want, what you're striving for, your goal is to do squares, okay? And again, when it's curved and when we do the dam in a second, you'll see it's not so easy, but really the goal is to have the cells as square as possible. So here it's pretty obvious. If you draw a circle inside, right, the circle should be pretty circular, not an oval. And again, the squares should be squares, not rectangles. So it's easier said than done, but that's what you're trying to achieve, okay? And in this case, so here's the equation that we'll use here, and this is basically a version of Darcy's law, right? So Q prime, again, remember, is a normalized flow, right? So it's Darcy's law times the depth of the aquifer, for example. So it's, flow per unit width, right? Whatever that is. So per unit into the page. So in this case, whatever that unit is. So for example, if this domain just flows into some river here, right, that would be Q per meter of river or kilometer or whatever, right? So this is our Q prime, basically the same definition as we've used in this class before. Now, the only thing that's new here, so H is the head loss, right? So that in this case, that would be 40 minus 24, so 16 feet. K is your hydraulic conductivity, so that's a given. You should know the hydraulic conductivity of your material. And the new things here are P, which is the number of flow tubes. And these can easily be counted here, 1, 2, 3, 4. So this is really, really important. I'm going to pause here. Flow tubes, right, are the intervals. So it's a picket fence sort of a problem, right? So if you have 3 flow lines, you'll get 4 stream tubes, right? There's 4 intervals. So really what you're counting is the intervals. Same thing for H, which is basically the number of squares between your equipotentials. So here it's like 1, 2, 3, 4, 5, 6, 7, 8. So 8 and 4. Okay, so again, remember, you're counting the intervals, not the lines. Okay, well then you can just, plug and chug. So if we apply this to our equation here, so K was 23 feet per day. We said P is 4 stream tubes, 16 feet of head loss across the domain, 8 squares, right? You calculate all this, that's 180 cubic feet per day per foot into the page, okay? Whatever, again, that distance is. And again, this is an example given in Feather, so you can go back and read, you know, those chapters. All right, so here's another example of how to build a FlowNet, so a little bit harder, right? More like a real-life example of a dam. So the way you start, right, is always the flow line. So, and like I said, usually you want to do 2 or 3, so let's do 3 here. 3 different flow lines, and if the domain is symmetric, right, everything is isotropic, etc., they should come out, you know, roughly the same distance on the other side. So now we can go under the structure. And again, this is not, you know, it doesn't have to be perfect. It's just to illustrate how to do it live. Once you have the flow lines, you want to do the equipotentials. So typically for a structure, you want an equipotential at each corner here. And usually I start with the one in the very middle. So I just divide this by 2 and I start there. The reason is because it's pretty obvious, right? This one needs to be perpendicular to the no flow boundaries. So it's going to be perpendicular here, and you can see intuitively that this is perpendicular to all my flow lines. So it's very easy to draw, it's just straight down. Now the corner ones is where it gets more complicated because you want to go as perpendicular as you can, but again, this is kind of hand drawn, so there's no good, you know, way to do this, sort of intuition. Now once you have those two, right, what you want to do again is strive for squares. So this is where it becomes important. The left one, the corner one, you know, you do what you can, but it's never going to be perfect. But once you have that, you want to divide these in squares. So you can see here, if I just did one in the middle, right, those things are never going to be square. These are like very rectangular and not very good. So what I'm going to do is divide this up in pretty much here. You can see I can do like 3 squares-ish, right? For circles, and again, this one is not perfect, but you know, they're not very rectangular, they're more square than rectangular, so that's good. So probably 3 is a good amount, so let's do that. And then again, that's going to be symmetric, so we probably want to do 3 each side, and again, you're trying to do squares and go perpendicular to, you know, all the lines. So square, square. And don't worry too much about the corners. This is, you know, probably good enough. And now we can apply our formula. So K is, Q. Let me do this again. So Q equals KPH over F per foot. Okay, Q prime. So here we said 1 foot per year. So P is the number of stream tubes. So 1, 2, 3, 4 again, times 4 times. So H is 20 feet, right? So there's a 20-foot drop between the reservoir and the river in this case. So let's call it 20. And then F is the number of squares. So 1, 2, 3, 4, 5, 6, 7, 8 divided by 8. And that should give you a number, you know, I didn't quite make the calculation, but that looks like 80, right? 4 times 20, 80 divided by 8, about 10. So 10 cubic feet per year, per foot. Okay, 10 cubic feet per year per foot of structure. Again, here it's more obvious what it is, right? It's per foot of dam. So if the dam is, you know, it's a low head dam across a small river that's say 100 feet across, right? That's 100 times 10 cubic feet per year that goes under that dam. Okay, so pretty quick and easy calculations. Here's the result from the book, and you can see this is basically what I did, right? So you have those 7 lines, so 8 squares. You also have the 4 stream tubes, so you would get exactly the same result. Okay, so this is again from the book. Here's another example in Excel, and I'm putting this slide here because you can see that depending on how many flow lines you have, the number of equipotentials should be different. So imagine we have this domain here. If we want squares, right, we don't need too many flow lines. Here, on the other hand, let's say we want it squared. Well, for those things to be squares, right, we need a bunch of flow lines because we have a bunch of equipotentials. So that's why I told you before, just do like 3 or 4 flow lines and then do those squares, and this way it's not like a crazy amount, right? But the point is, when you use this equation, right, there's a correlation between P and F. So if you take 3 flow lines, right, you'll have less equipotentials. If you take, say, 10 flow lines, now we have a bunch of equipotentials to get to those squares, but that means that the ratio P to F, right, should be about constant if you do your problem, correctly, which means the Q prime you calculate, no matter how many flow lines you use, should be the correct one. Okay? I think I'm going to leave this here, and then maybe I'll restart the video to show you a couple of other calculations we can do. But this first video was, just build the FlowNet basically, and now I can show you examples of FlowNet applications.